So far, we have been talking about explicit methods where at each time step or each step, we can determine the value of the state based on the previous value of the state. There is also implicit methods that are needed when we are dealing with boundary value problems where there are multiple values at different parts of the domain that are known to us. So in that case, we cannot just step through the process as we do it in the explicit method, but instead we have to create a system of equations and then solve those system of equations to find the answer to the differential equation. So here is an example of heat transfer that requires using implicit method. Now we know that the heat transfer is given by a second order differential equation. So under steady state condition, the temperature, spatial temperature variation along a material depends upon the sources as well as the ambient temperature around it. So for example, in this case, if T1 was hotter than T2, the heat will be flowing from T1 to T2 as well as going into the ambient air, surrounding air, which is at a lower temperature. So if we are trying to create a profile of temperature, so what is the temperature at different points along this rod, we'll have to use a numerical methods. But because the values that are known to us are at x is equal to 0 and x is equal to L, which are the boundary points, we cannot just start from here and then keep measuring the next value because we have to hit the correct value on this end. So for that purpose, what we end up doing is we end up creating a system of equations. So if I want to implement this as a numerical method, I can convert this second order differential to a second order difference, and then through a little simplification I can convert this into a linear equation that depends upon the current, this time step, or this point, the previous point, and the next point. And so if I start from this end, I can create this equation for each point, and this will end up creating n or n minus 1, in this case n minus 1 equations that I can solve through simultaneous equation method. So suppose that we set the delta x to be equal to 2, and so we are to determine the value of temperature at 0, 2, 4, 6, 8, and 10 units of length along this rod. And then the corresponding temperatures are 40, T1, T2, T3, T4, T5, where T5 is 20. So these values are given on the previous page for this problem. And if we take our difference equation and implement it for each one of these points, of course we can't do it for x0 because there is no x minus 1, but we can start from x1 and go all the way to x4. And here are those 4 equations that we can create. Now since we know T0 and T5, we can take those to the other side, and this gives us 4 equations in 4 unknowns. And if we write these in a matrix form, we get this A matrix, which is a tridiagonal matrix, the T matrix, which is the T1, T2, T3, and T4 temperature values, which are the function values that we are trying to determine, and then this can we can call this as the B vector. So this formulates AX is equal to B problem, which we already know how to solve in MATLAB. So let's implement this in MATLAB. Again, we know the ambient temperature, we know the temperature on the left side and the right side, and we know the value of h, which is the constant of heat transfer. And then we can create our domain from 0 to 10 at an interval of, let's do the way we have been doing for the interval of size 2. And let's create C1 and C2. These are just C1 is the diagonal term of A matrix, and C2 is this term here. This is just for the purpose of simplifying our calculations. And now we can create a tridiagonal matrix. We have done this before in another lab. If you have forgotten, then look for the help for gallery, and then in particular look for the tridiag. Now if you print A, this is the matrix A. We just computed it. So its off diagonal values are 1, and then the diagonal values are computed using 2 plus delta x squared h. Similarly, we can calculate the B matrix, and here I'm using a command called repmat, which means I'm replicating the value of C2 over n minus 1 by 1 matrix. So make sure you look at the help of this function to learn more about it. And then I'm adding T0 and TL, T0 to the first entry, TL to the last entry, which is right here. T0 to the first entry, TL to the last entry, and we're subtracting it. So this will give us our B matrix. Okay. And now in order to find this matrix, we call it P from our previous application. We call it the parameter matrix, but it's technically temperatures. So this is pseudo inverse times the B matrix, and that gives us these temperatures. Now these are the temperatures on x1, x2, x3, x4, but we know that the x0 temperature is in our case 40, and x10 temperature is, or x5 temperature is 200. So we can add those values as well to this array. So first create X matrix, which is 0, 2, 4, 6, 8, 10, and then we also create the T matrix, which is the answer that we just found here, along with 40 and 200 concatenated to it, 40 and 200. And then we can just plot these values, and this is the profile of the temperature along the thin rod. We can reduce the step size and rerun this code, and you can see as you run it on a finer grid, you get more and more profile of the curve. And if you look at the equation of the original equation that was given to us, you can see the H parameter is basically determining that how fast is this temperature cooling. And so it depends upon, it's directly proportional to the difference between the temperature of the rod and the ambient temperature, and also this H basically is the heat transfer coefficient that tells us at which rate it dissipates to the surroundings. So you can play with that parameter as well to see how it will change the shape of the curve, and what and then how does that determine the profile of the temperature. So this method basically teaches us that when we have a problem where the boundary conditions are given, and often Euler's method will not work for us. It can work through another approach called shooting method, but in this case, when we have an implicit problem, then we can always reformulate this problem into an AX is equal to B, and then use the least squares approach to estimate the function by using the pseudo inverse of the matrix. So that concludes the implicit method approach.